Buenas tardes.
Good evening. On behalf of the BBVA Foundation, it is a true pleasure to welcome you to our headquarters in Madrid, and thank you for being here at this conference on climate change by Professor Bjorn Stevens. This talk and the dialogue that we're going to have, the debate on the 9th here between Carlos Duarte and architect William McDonough, are part of the activities that the BBVA has organized to join the COP25, the Climate Change Summit. The environment is one of the key areas of our work at the BBVA for 2 decades. In 2000, we selected 2 essential issues that we have continued to work on: the conservation of biodiversity and climate change. They're associated to each other and must be focused on specifically. In addition to giving support to people, teams, and disseminating environmental awareness in society, we have 2 families of awards that recognize these 2 areas. Since 2004, the Foundation BBVA Awards to the Conservation of Biodiversity recognize conservation and awareness-creating activities in Spain and Latin America, and for 2 years now globally. And this year, we have created a World Award for Communication, the Biophilia Prize, which in its first edition was given to the BBC environmental correspondent Mark Macra. Our awards, Frontiers of Knowledge, recognize excellence. 12 of the people that have been given this award were later given the Nobel Prize in 8 categories: ecology, conservation of biodiversity, climate change. And in the 11 editions of this award, I will just give you a few names of the people: William Broker, Edward Wilson, Susan Solomon, William Dorhaus, or Annika Seleninen. And since the beginning of these awards, Frontiers of Knowledge, more than a decade ago, Professor Stevens has been president of the International Jury in Climate Change. Bjorn Stevens is the director of the Atmosphere Department within the Terrestrial System at the Max Planck Institute, the main organization, public scientific German organization, where he is also head of the Meteorology Department. He's professor at Hamburg University and was professor of atmospheric science at the University of California at Los Angeles. We are very thankful to him. With the tight schedule he has and his busy life, he's accepted our invitation to share with you his view and vision on the status of climate change science, which is the topic of his latest paper, which is about to be published. At the end of this talk, you will have the opportunity to ask him, Professor Stevens, your questions directly. Without further ado, I invite him to come to the rostrum and take the floor. Professor Stevens.
Thank you very much. I should have the microphone so you can hear me okay. And I'll be walking around a little bit. And I'll try to speak slow so the people who are listening on audio can catch up once in a while. First, I wanted to say thank you to the Foundation and to Silvia. It's really a great pleasure to be here in Madrid and to do the work with the Foundation that they've started with these awards, but also with COP25 as it came here to Madrid. Sort of the response of the Foundation and other organizations to try to make this a successful event has been tremendous. And so it's really great to be here to do things with the Foundation and try to promote many of the things that the Foundation tries to promote, from understanding of science, the importance of science in society, but also different cultural activities that they organize. So thank you very much for the opportunity to be here tonight. And thank all of you for your attention. It's really an honor to be able to take part of your evening to tell you a little bit about how I think about climate change science. So I won't be very much help to you in terms of what to do politically, but I hope I can explain some of the science to you. And at the end, I have a lot of time. And so if you want to talk or discuss or have questions or have controversial ideas, feel free to ask them. We have a headphone here, so people can ask the question in Spanish and it will be translated back and forth. So that's the plan for the night. My talk has about 22 slides and it's about 45 minutes, so you can kind of pace yourself. And the idea that what I wanted to do tonight was do something that normally we're not allowed to do as climate scientists so much, is to tell you about some of the things that we don't know. So often climate science is always telling everybody all the things that we do know, because we have this feeling that that's important for how we behave in society. But there's many things that we don't know. And I want to tell you about some of those, but I also don't want you to become confused. We do know a few things, we know them well and they're important, and based on those things we should take certain actions if we're prudent. So just because we don't know everything doesn't mean we don't know anything. So in the beginning what I will do is I will tell you about some of the things we know, just to remind you of that, and then we'll talk about the more fun things, which are the things that we don't know. So the things that we do know, I should use this pointer here, the things that we do know, they warrant action. Based on what we know, we should do things, and I'll talk about those. But there's many things that we need to know to make our actions more effective. So here's the young woman of our time, Greta Thunberg, and she says, listen to the science. So we're not going to have a debate about Greta Thunberg, what you think of her or not. But I wanted to take her phrase, listen to the science, and use that to explore what does that mean? What does the science really know? And what does it not know? Because if we listen to the science, we need to be able to discriminate between what the science says and maybe what individual scientists say. And if we think about what the science says, it tells us, and I will go through the chart in more detail, it tells us that the world is warming and CO2 is the cause. And it tells us that we understand this pretty well. And this is an example. It's from a paper that, this is Bill Nordhaus. He got the BBVA award for climate change science 2 years ago, in 2017 edition of the award. And then he won the Nobel Prize in economics a year later. And he wrote a report in 1977. So in 1977, the world was colder than it had been in a long time. And people were even talking, some famous scientists were even began talking about maybe it's the beginning of a new ice age. And he wrote this paper in 1977, and what he did was he tried to take the latest ideas at the time about how carbon dioxide affects climate and work out how that would change in the future. So through the 1950s and the 1960s, people had been trying to work through the science of how CO2 affects the transfer of energy through the atmosphere by radiation, radiative transfer. And they had more or less worked out a theory of how climate change might result from increasing CO2. And the theory was quantitative. And it was enough information for Nordhaus, who wasn't a physical scientist, to take that theory and try to extrapolate it forward in time and guess what would happen in the future, and then try to imagine what we should do about it in terms of economics, in terms of energy policy. He was working at the time as a young man as a postdoctoral fellow in an institute in Austria, working on economics and energy policy. And he thought, oh, this is neat stuff, CO2. And he drew this graph here. And this graph, if you look at it, this is temperature on the y-axis. So 1 degree warmer than in the distant past, and 2 degrees, 3 degrees, 4 degrees. And he took his best estimate of temperature here, this is the black line, and he drew how it had changed over time until he wrote his report, which was about 1975. You see, it had been going down since about 1950. And now we understand the reason it went down was because there was a period of strong volcanism starting in about 1960, several volcanoes, and there was a lot of particulate matter in the atmosphere from industrial pollution. And so most people think that's why the temperature was going down here. But there was this idea of the scientific community that had been worked out by other laureates of the BBVA that temperature should rise with CO2. And so Nordhaus drew this curve here, this dashed curve. This is in 1977. And he said, this is how I expect CO2 to rise. And when the CO2 concentration is about 50% more than it is today, I expect the temperatures to equilibrate at about this value here. And so he tried to imagine the future. This blue line is the sort of rough best guess of how it actually has changed. So 40 years later, what you see is this is a pretty good prediction because it was done with very simple tools, and he gets about most of the answer right. At this point, we didn't even know the sign. We didn't know if it would be going up or down or anyway, and he drew the curve going up, and he got it at about 80% right. you could see his temperatures are a bit warmer than it actually is. So lately in the papers, people have been fond of saying that climate is changing faster than scientists thought. That wouldn't be true in the case of this graph here, where actually he thought it might be a bit warmer by 2020 than it is today. But overall, it's a good prediction as far as these things go. He also drew two other lines. I made them in red and blue. They were black in the original figure. In the blue line, he said, well, the climate sort of varies by a certain amount year to year, decade by decade. And to really talk about a detectable, noticeable change, we probably need about a degree of warming. That kind of gets us outside of what would be a normal variation. And if we don't want to be stupid, we probably should try to keep the temperatures under 2 degrees, was his idea. And here you can read, if you like this quote. He basically just says it seems reasonable that we should try to limit temperatures from getting more than 2 or 3 degrees above what they were over the last 100,000 years. Because once you get above this temperature, you start having temperatures which are different than we have any experience with. So you really move the Earth to a place where we have very little sense of how it will behave. So he said, well, it's just a reasonable thing. 2 degrees would be a good target. Later, this has been taken up as this 2-degree target that we have to keep the world under 2 degrees. That's not a real strong scientific statement. It's just a sort of gut feeling that the warmer we get, the worse it gets. And a good number might be 2 degrees. And it goes back actually to this paper. And then later, after he wrote his paper trying to figure out what to do, how to change the economy, what this would affect, he suggested taxing carbon. He also said these other questions, which are important for later on. He said the central question for economists, climatologists, and other scientists remains, how clearly are the projected changes in, or the uncertainties about, the climate likely to be? And therefore, to what level of control should we aspire? So only if we know more precisely how things will change might we be confident trying to more tightly control how the system evolves. And he also recognized how hard it would be to get agreements, because changing something like energy policy is a global action, and our ability to govern ourselves globally is small. So this is what the science says, and basically it says that 42 years later, it says he was more or less right in what he said, and other scientists at the time. And if you really, I tried in these slides, they'll be on the website, but I tried in the slides in a few words to really specify what I think the main things that the science is very confident about. And they're fairly general if you look at them. That we're very confident that Earth's surface temperatures are rising. The heat content, the enthalpy of the ocean is increasing. Ice is retreating. The seas are advancing, they're rising. The Arctic is warming faster than the rest of the planet, and land is warming faster than water. With warming, we also are pretty confident that comes the expectation of an amplified hydrological cycle. And a simple way to understand the hydrological cycle is that if you had to stand on a rainy day, would you rather stand in the north of, it'd be cold, but in terms of just getting wet. So imagine it's a rainy day. You could be in the north of Norway and it's raining. How do you picture that when it's raining in the north of Norway? It doesn't seem very intense. It's sort of like this dreary rain. It's not a lot of rain. Or you could be in a tropical rainforest and it's raining. There you imagine it's gushing wet. And the opposite when it's dry. If you have to put your hands in a hand dryer, would you rather put them in a cold hand dryer? It takes a long time for them to dry off. Or if you put them in a hot hand dryer. That's basically the physics of why the hydrological cycle will be intensified, is that the ability of the atmosphere to process water is much greater at higher temperatures, and so we expect hydrological extremes to happen. So these are things that we expect or observe. We also know that the burden of greenhouse gases, mostly CO2, but also methane and N2O, is increasing. The ocean is becoming more acidic, and we understand that humans are responsible for that. We also know that all of this is happening at rates which are unprecedented. They're super fast, geologically. But there's nothing that's so slow as geology. So geology is very slow. So being very fast compared to geology is like getting in a race with a snail and winning. I mean, you don't have to be very proud to be fast compared to geology. But it is fast compared to geological or evolutionary timescales, which has implications for the natural system. So each one of these statements can be backed up by many lines of evidence, It's not that it's just one study or one scientist. Many scientists have looked at these issues again and again and again from different perspectives. People have objected, they have said it's wrong, people have looked at why it might be wrong and found out it wasn't wrong. And these are some of the prize winners who are associated with some of the statements that you see above. So the point here is that 40 years ago, Nordhaus kind of sketched out how the climate system would evolve based on very rudimentary theories. There were many, many reasons why those theories could have been wrong. We spent the last 45 years investigating every one of them, and we're left with more or less the same picture we started with. So that's how science goes. It's not so fast. We're critical, we test things, and we end up with this picture. So if we look at that, and this is the part where I say this is what we know, and I get to what we don't know, which is more fun. What we know is that we're changing Earth's climate in profound ways. And these changes will be very difficult to reverse. Taking CO2 out of the system is very difficult. It's very energy intensive, and you have to figure out what to do with it once you get it out. The consequences of global warming and ocean acidification are becoming tangible. One can debate how much different things are associated with global warming or not, but we have the sense that it's impacting the way we live our lives. And continued warming, it just keeps going and going and going and going, and time goes by. Continued warming carries risks. Now, a risk doesn't mean bad things will happen. It means bad things could happen. So continued warming poses risks. And eventually, if you're ready to extrapolate for very, very, very long periods of time, it's also clear that it will change our planet in ways that make it hard to live here. But this, again, is in the far future. So because of those things, when we say listen to the science, because of those things, I would say it seems prudent to do all that we can. And here I would be modest. I would say, people ask me about solving the problem, and I said, well, I would be really happy if we stopped making the problem worse. And right now we're making the problem worse because the amount of CO2 that we put in the atmosphere is increasing year to year. So it seems prudent to at the very least, to stop making the problem worse. But that really addresses only one question when it comes to the big questions we face as a society with respect to climate change. I call it the mitigation question. Mitigate, should we act to prevent warming? And you can pose these, sometimes in mathematics you can talk about solving equations, differential equations in the weak or the strong form. So people who are in mathematics might be familiar with that. And the weak form is always easy, and the strong form is a lot harder. And the weak form of the mitigation question is the simple question, should we mitigate by reducing emissions? And I think the science is unambiguously, unequivocally clear, yes, we should. The hard question is, how much should we mitigate? How quickly should we mitigate? How rapidly do we need to change these things? And what happens if we don't? So that's the hard mitigation question. And here the science is much less helpful. And the other question is the adaptation question, is that the world will warm, even if we stopped emitting, stopped increasing CO2 output today. There's warming that's still not realized in the system. The system's out of equilibrium, and as it adjusts to equilibrium, it will continue to warm. So what does that mean? What will happen with that warming? How will we adjust? How will we adapt? How will we prepare ourselves? What sort of surprises might we have? That you could call the adaptation question. So the first question, I think, was easy, but it took us a long time. We solve it. The science is there. We don't really need to discuss that. The next two questions are hard, and they really pose great challenges for the science. So as scientists, we're very proud. We pat ourselves on the back because we helped society answer the first question. But there's big work to do for science in answering the next two questions, and that's what I'll talk about for the rest of the talk today. Here's three examples of things that the science doesn't tell us. So imagine we say we want the world not to be warmer than some number. You can all vote or listen to the news or whatever. Normally people pick the number 2. It's a nice number. It's my wife's birthday, 2, the 2nd of February, 2-2. So people pick the number 2. We don't want the world to be warmer than 2 degrees. It goes back to Nordhaus. And then you could ask yourself, well, if we don't want the world to be warmer than 2 degrees from the past temperatures, how much CO2 can we emit? How much carbon can we emit in the atmosphere? And that depends on how sensitive the temperature is to a given amount of CO2. How much does it warm if you add a certain amount of CO2? That's something we call the climate sensitivity of the planet, how sensitive it is to a certain amount of emissions of CO2. And in this graph here, what I showed was this is now the 6th generation of people building models of how the climate system works, trying to put all their knowledge into models one way or another and estimate how sensitive the model is to a doubling of CO2. So if you double the amount of CO2, would the planet warm by 2 degrees, 3 degrees, 4 degrees? Nordhaus said 2.5 degrees. About 10 years ago, when people did this exercise for the 5th time, the answer came from 2 to 4.5. Now that they're doing it this time with the models again, it says 2.5 to 6 or so, 5.5. The point is not that these numbers, you shouldn't take these numbers too literally. The point is that there's just a lot of uncertainty, even if you just believe these models. I think there's good reason to think it's more down here than up here. But if the climate's very sensitive to amount of CO2, then we can't put very much more carbon into the atmosphere before it gets warmer than our goal. Remember, our goal was we want to keep the temperature less than 2, so how much carbon can we put in the atmosphere? So if the planet is as sensitive as these models, it really says we're almost done. I mean, we can't put hardly any more carbon in the atmosphere. Whereas if they're as sensitive as some of these models, then it says that we actually can put as much carbon in the atmosphere as we've already put in it. We're not even half done. It's a huge difference. So when we talk about this mitigation, how quickly we need to act to reach a goal, there's a lot of uncertainty because the models are very unclear about how sensitive the planet is to the amount of CO2. They all show it warms, and they'll keep warming the more CO2, so that's not in doubt. We should reduce CO2, but how quickly that happens and how much that happens is unclear. So that's one thing that the science doesn't help us with, the strong form of the mitigation question. There's another. So this graph is fairly complicated, and what it shows is the Earth. We're up here in Spain, Africa, South America, Australia. And this shows how much the rain changes. So it's blue and green, that means it's increasing the rain, and the brown means it's decreasing the rain. And it's these same types of models which people have used to say, how does the rain change? And basically what you see is wherever you see little dots, the models are fairly confident. That means they all kind of do the same thing. They increase the rain. And wherever you see slashing, that means the models do all very different things. And so they're not confident at all. So the first thing is, just because models agree with one another doesn't mean they're right. In the end, the models are fairly similar, so we kind of expect them to agree. But when they disagree with each other, then we have even bigger problems. So we like them to agree because it sounds like, well, there's something that we can understand there. And here what you see when it comes to patterns of changing rain, the whole tropics is mostly covered by hatched marks. That's where the rain is variable. We have dry regions and we have wet regions. We don't really know what will happen to these regions in the future. So will the dry regions expand? That's generally what people think. But how much will they expand? Will the wet regions contract? That's also what people think. But it's based on a very imprecise tool that we don't have a lot of confidence in. So when we ask how the weather changes, particularly in the tropics, there's very little we can say with great confidence about the future. And this matters if we want to adapt to climate change. If you're talking about small island nations, or if you're talking about nations or areas which are reliant on rainfall, or if you talk about, if people remember what happened when the Sahel, this region in Africa below the Sahara, dried suddenly in the 1970s and the mass starvations that were associated with that, or if you're worried about the rainforest, if it's really going to dry out and burn away. I mean, these are things that you would like to know, but we really don't have a good idea about. The other thing is, I don't know if people have been following the press. Sometimes when you read the press, I'm going to do a poll for you. This is fun, because I asked this at dinner. We have Thanksgiving in the United States. I'm American, but I live in Germany. And so we celebrate Thanksgiving anyway. And so we had a Thanksgiving dinner. And I asked, it was my daughters there, and there were a bunch of other teenagers, and then their families, so there's 12 of us. And I asked people, they're concerned about climate change. And I asked people, imagine climate change, it warms much faster than people think. The climate change is warming, really at the upper end of the worst scenario. It's warming as fast as you can imagine. Greenland will melt, clear. Will it melt in 50 years, 100 years, 200 years, 500 years, 1,000 years, 5,000 years? What do you think? So everyone make an answer for yourself. The world is warming so that after a few hundred years, the temperatures are not 2 degrees warmer, they're 10 degrees warmer. So if you take the best science and you ask how long, if Greenland melts really fast, when will it melt? So how many people think it will be within 100 years? Does anybody think that? 200 years? 50 years? So the answer is if Greenland melts really fast and temperature gets some people are willing to say it might melt in as much as 1,000 or 1,500 years. But a much more prudent thing would be to say even if it's melting, it's going to melt in 10,000 years. So we're talking about timescales which are enormous. But if you listen to the public debate, sometimes it's hard to put these in perspective. So we have this feeling that if the world is not stopped from becoming greater than 2 degrees, we've all failed. It's a catastrophe. But is there, other than it being my wife's birthday, is there anything special about the number 2 when it comes to climate change? This is something we would also like to know. And here I drew this because we have this idea of the 1.5 goal. We'd like temperatures to be less than 1.5 or less than 2. And so people ask, what's the difference between 1.5 and 2? And normally I would say, well, the difference between 1.5 and 2 is that if you multiply 1.5 here by 4/3, you get 2. So the difference is just 33%. That would be a mathematician's way of saying that's the difference between 1.5 and 2. But when we talk about potential worst case scenarios, the hypothesis is that no, actually 2 is much larger than 4/3 times 3/2. So that something special happens. But again, the science really can't answer that. That's something we're not at all confident about. And so it's easy to speculate as to what might be a worst case scenario. Those are good things to know, but one shouldn't confuse the worst case with the most likely case. So the world is warming, that's not good, but there's very little science to support the idea that somehow something magically changes at 2. So this is what the science doesn't tell us yet. So why? So we have these problems. We'd like to know how much CO2 we can put in the atmosphere to stay below a certain amount of warming. We'd like to understand how the weather patterns might change. We'd like to know if we're going to have a cascade of catastrophes that happen when we reach a critical temperature. But right now, we're not in a position to answer any of those questions. And my question for you is, why is that? And what can we do about it? So the answer why that is, I'm going to give by a form of an example. And the answer is up there. The answer is because the models that we use to help interpret data, the models that we use to predict into the future, are simply inadequate to answer these questions. And here I want to give you a very vivid example of that, which these are examples people don't like to show because it tells you what we don't know, but it's fun. So this example is, as a climate scientist, often what we do when you have a hard problem, some of you might know this, I guess probably people here are trained in math and physics, and they know the story that when you have a really hard problem to solve, the first thing you should do is try to make it easier. So if you have a hard problem that you don't understand, you try to turn it into an easier problem that you do understand. And you keep doing that until you have something you can understand and then try to work your way back up. Something we do in climate science as well, and that's what's shown in this calculation. So normally we have these very sophisticated models which have ocean currents, and they have vegetation which grows when it rains and dies when it doesn't rain, and fires which rip through, and dust which is transported, and mountains and ice sheets, and all of these things all interacting with each other in very complicated ways. But we said that's all too hard, so we'll make a simpler problem. And this problem is what we do is we just we get rid of all of the land, and we cover the earth with water. We don't let the water move, and we specify its temperature. We say the water, you have a certain temperature. So we've gotten rid of enormous amounts of complexity. The whole earth is just water covered with a specified water temperature that looks sort of like the present day temperature. It's warmest at the equator and it cools near the pole. And then we take that earth and we run the model, and it produces rain. And then we do the experiment with the model. This is one of these sophisticated models that we use for our assessments of climate change, but it's run in a simple configuration. And we take that model and then we increase the temperature everywhere by 4 degrees. And then we see how much it rains. And then we take the difference and we compare them. And that's what you see here. So this is the difference in rainfall from this aqua planet, water world. It's the difference in rainfall from a world that's 4 degrees warmer, than the control world. And what you see in the model is it rains a lot more on the equator. The rain kind of contracts to the equator. And on the flanks of the equator here, you have these very strong dry zones. So based on this model, you would expect the rain bands in the tropics to kind of contract at the equator and dry air on either side. You also see that the extratropics, Spain would be kind of up here, right on this boundary. But these mid-latitudes here are mostly dry, or not much is happening. And once you get towards the poles, you see it is wetter. So in a warmer world, the poles are wetter. The equator is much wetter. This ends up being wetter. The dark blue is 3 millimeters a day. And that doesn't mean very much to you, but that's about the average rainfall that you have in a year. So it's increased by what, the rain isn't distributed evenly. It's much more in the tropics. But it increases by about the global average amount here. And it decreases by about the same amount here. Okay, good. So you see that's one model. But what if you do this experiment with another model? And you have to remember, our models are more similar than they are different. When it comes to the world, the real world is complicated. It looks like this. And our models, if this was distance, our models would be over here. Model 1 would be this far away from the real world. It makes many approximations. It's a very different thing. And model 2 is sort of over here. So the models are much more similar to each other than the real world. And we're trying to solve for how this thing over here behaves. It's very far away. I hope that makes sense. So we're going to do another model. And then we say, OK, at least if the models agree, then we have confidence that maybe it's being driven by the physical assumptions in the model. When we do that, and this was a paper we published in Science now 6 years ago, that's the answer we get. So you see, if you live in the tropics, it's completely useless. I mean, these tools. Because this one says it's going to rain more at the equator, and this one says on the equator, well, maybe there's a little band where it gets a little wetter, but mostly it gets drier. And then on the flanks of the equator, instead of the rain band contracting, it seems like the rain bands are spreading out. So if you look over half of the world, the tropical half of the world, these two models are night and day. They're just completely different. This doesn't give you a lot of confidence that these models really know what controls the rainfall and how that will change as you warm. If you live in the polar regions, here the models are actually good because the assumptions the models make are best founded for the high latitudes. So the way they use the physics is best in the high latitudes. And here you see that both on the poles, they both agree pretty well. So there's some consensus there. So you could say, well, you just pick two models which are kind of extreme, but when you look at all the models, it won't be that bad. Okay. So here's 6 models. And if I asked you to draw pictures, if I gave everyone a piece of paper and I said, just color it in, I don't think you would be so creative to come up with so many differences as you can see on the screen. So you see all of these models. This one, these two both rain at the equator, but this is very dry on the flanks. This is dry in the middle. This is sort of asymmetric. This is, who knows with this one? And this is, yet something again. So the models are very different. And that's because, and that's what you have to understand, is the models we use to simulate the climate are partially based on the laws of physics. There's the fluid flow, which is quasi-horizontal, which moves heat from the equator to the pole through instabilities that develop in the flow. These are storms. Those are done using laws of motion that we know to be true. But there's large parts of the models which are based on sort of, finger in the wind. You're kind of saying, well, in the tropics, we know when the water's warm, it should rain, and we make up little empirical rules that we do our best, we try. And it turns out for very important things, these rules matter. How you come up with the rules has a huge influence on the results. So we're not confident. We call this activity parameterization. It's a technical word. Parameterization, a parameter is a number that you fix, like 8. And a parameterization is instead of trying to represent the rainfall in the model the way rain really works, is you try to model it or approximate it statistically with some parameter that you set, which governs the relationship, for instance, for the sea surface temperature, the temperature of the ocean versus the temperature in the middle atmosphere. So there's sort of statistical rules of thumb that people try their best to develop physically over many, 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 many years. And you hope in the end that the difference assumptions don't make a big difference to the answer. But what we found out over the last 30 years is it does. This is an example of how a parameterization works. So this is a simulation we did with two models. One model is the type of model we use to simulate the climate system. And what's shown here, this is height in the atmosphere. So this is near the surface, and this is at about 20 kilometers in the atmosphere high. And this is the Alps, and this is looking towards North Germany. So it's a long section as a storm moves through North Germany. And we only simulate one day just to see how the model behaves. And in the parameterizations, you have little rules. The model, for a climate model, it has a very, we talk about to solve how the weather evolves on the Earth, we have to break it up into pieces. And for a climate model, the pieces are very large. And so in each large piece, we come up with a rule for how it rains. And so in the climate model, what we say is, should it rain? And then we say, yes, it should rain. And then the next rule is in the computer program that says, well, how much should it rain? And then it calculates how much it should rain. And then it calculates how much water is there. And if too much water is there, then it leaves the rest in the clouds. So it makes rain, and whatever doesn't fall out as rain is left, and it makes a cloud. And so here in this graph, what you see is the blue is the rain, and the white is the cloud, and the pink is the ice clouds. So if the cloud is cold, then it's an ice cloud. In the model, because of the way the rule works, it's actually the opposite of how the world works. So in the world, normally if you make rain, you make a cloud. First you make a cloud, and the cloud stays there, and eventually the rain falls out. In the model, it's easier to say, let's make the cloud after the rain. So you make the rain, and whatever doesn't rain is left to make a cloud. And so you get funny physical things, and so this is what the clouds look like in the model. They're not completely ridiculous. But this is when you actually break the pieces into very small pieces, and you can simulate how the air motions move and how upward air cools and condenses and forms rain and forms cloud and then forms rain. And so you see here underneath the rain, you see very strong turrets of very strong convective clouds moving up here and the rain falling through. And it's a completely different picture in terms of how the cloud and the rain and the ice clouds interact with one another. In this one, they're connected through the circulation, through the motion, than in this one. So we had hoped for a long, long time that we could solve the climate problem by using tricks for representing things like rain. And what we found out is that we're not so lucky. We might have to really use the physics, which is difficult, but now possible, and I'll get to that. I want to give another example. So I said in the models, we have a hard time representing where it will rain. The other thing that's very difficult when we model the climate is deciding how cloudy it is. So clouds form because air moves upwards. It cools, the air condenses. Sometimes the clouds rain, sometimes they don't rain. And if you think about the climate system, the job of climate is on the Earth, we get energy from the sun. It rushes in mostly near the equator, mostly near the surface. And the energy of the sun warms the surface, and then that's redistributed and lost back to space. So climate is really about this exchange of energy. We get energy from the sun, and then we lose energy to space through infrared radiation. Clouds modulate or affect that relationship. So if you have a lot of clouds, then you don't get as much sunlight. If you have few clouds, you get more sunlight. How many clouds should we have? No one really knows. I mean, there's no theory of cloudiness. How many clouds did we have in the past? Nobody knows. So a big problem for climate models is when you look at the clouds, they don't happen for real physical reasons. They're, again, this sort of rules of thumb, is what governs cloudiness. So when I came to Germany, I had the opportunity to set up this measurement station on Barbados, because Barbados happened to be, here, this is the measurement station, and it's on the east coast of Barbados, a place called Devil's Point. And it's nice because Barbados is in the Atlantic Ocean at about 13 and a half degrees north, and about 60 degrees west. And if you look from here, and if you could see really, really far over the curvature of the Earth, 5,000 kilometers later, you would see Senegal. You'd have to look a bit to the north. So it's right there at the edge of the trade winds which took the adventurers across the oceans, blow from the coast of Africa towards Barbados. And it turns out that the clouds, you see outlines of them here, that form in the trade winds are really important for how different climate models represent climate change. In some models, when the Earth warms, they make a lot more of these clouds, and it doesn't warm as much. In other models, when the Earth warms, there's much fewer of these clouds, and it warms a lot. Back to that first graph. So we said, well, maybe we should measure these things and see if we can learn anything. And so since 2010, we've had this site, and it's been growing. It's much bigger than it is now. But this is a radar and LiDAR, another small LiDAR, small radar, lots of radiation camera instruments here measuring the clouds. And I'm going to give you a picture of how that looks like in a graph. So this is from the radar in the top, and it's just 1 day here, every hour. And what it shows is height, so it doesn't go very deep in the atmosphere to about 3 kilometers. So a tall mountain might be 4 kilometers high. I think the tallest mountains in the Pyrenees are right at about 3,000 meters. So that's 2,000 meters or 2 kilometers. And what you see here in color is that most of the clouds like to form at a height which depends on how moist the air is, about 700 meters. And you see that in a day. Often you see the clouds, their bases are sort of at a constant height. They may go different heights, but they seem to all form at a constant height. And that's what you see here, is that most of the time the little blue ones start at the same level. But once in a while you see these orange streaks. And that means there's really big drops which are falling down. And this is from the radar. So this tells you this cloud is, when you see the orange going to the ground here in the middle, this means this cloud is raining. So when the clouds get very deep, they start raining and the rain falls down. And once in a while, the deeper clouds seem to kind of spread out into these thin layers which are spread across. So that's what you see here. So we've been there for 10 years, so you can look at days like this, and well, every day, and you can just accumulate what is happening with the clouds. And what you find is you can break these clouds. This was done by a master's student working with me from France, Octave Tessiot. And what he did was he said, let's count all these clouds which have their base here at this level. Let's call these clouds, he called them dry clouds, and he colored them orange, dry cumuli. And he said, anyone which is raining, let's call it a moist cloud. And he colored it blue. And the ones which are up here kind of separated from the bottom, we'll call them stratiform clouds, and we'll color them green. And then you can see how many of these orange ones there are. This is over many years, how many of the orange ones we are, how many of the green ones we are, how many of the blue ones there are versus height. So here this says there's lots of orange ones, and mostly the maximum number is at about 1 kilometer. And the green ones, which are the stratiform clouds, are mostly here at around 2 kilometers. And the other ones get even deeper. And then you can go on the daily cycle, and you can look at every hour of the day, and you can see how the clouds change. So what you find here is that if you look at the orange ones, at about the middle of the day when the sun is most intense and you're absorbing a lot of heat in the surface ocean and in the air around it, these little clouds kind of die off. They go away. So you see they become a little bit less. It goes down. And what you see is that the sun starts going down again and goes up, then the little clouds get bigger. But these stratiform clouds, they also start increasing. And through the night, they increase. So that if you add all of these up and you look at how cloudiness changes, it's made of 3 parts. But you see it in the early morning hours, you have the most clouds. And that's because these guys like the nighttime hours, for reasons we know, but I won't explain to you. These clouds like the nighttime hours. And then during the day, during the sunlight, the clouds go away. So you can take a model, a simulation, a numerical model, and you can try to represent this. And that's what happens here. But this is a model where I break the Earth into pieces which are 150 meters across, sort of like this complex, not the room, but the complex that we're in. So it's a very fine scale model where we can simulate how the air moves. And you can do that same picture again. This is the hours in the day, so 9 o'clock in the morning, that's noon local time. This is sunset, and that's sunrise. And the color tells you how cloudy it is. And going up this way tells you where the clouds are. So what does this tell you? The fact that it's green here. It tells you that you have lots of clouds at 5 in the morning, that's down here, at this height of about 2 or 3 kilometers. And the fact that there's no green here, that tells you that there's very few clouds at 12 o'clock in the day near this cloud base level. This picture looks a lot like this one. The clouds up high tend to peak in the early morning hours, and the clouds on the bottom go away at noon. It tells you that's how we do the science. We collect the measurements, we make a model, we try to do that, and we look, okay, if we have a model that can simulate how the world behaves, it actually can represent the reality pretty well. But that's not a climate model on the right-hand side. I'm going to show you what the climate model says, and that's what we see here. So here what we can do is we can take this same picture, which is actually the one on the far right here that I showed you before, and we can say instead of having little pieces where we simulate all of the air motions that make clouds, let's make them a little bit bigger. And then what we see is this picture kind of looks like this one, but it's a bit different. And then we make them a lot bigger. This is sort of 10 times bigger, and this is sort of 20 times bigger. But if you look at these figures, I would say they're by no means perfect. Quantitatively, they differ quite a bit. But they're kind of trying to do the same thing. They're not succeeding. When we have the model which is 20 times bigger chunks, it really has a hard time representing what this model does, the finer scale model. But it's trying. You see the clouds are going away at noon and they're building through the night and maximizing in the early morning. So there's a hint that the model isn't perfect, but it's trying to do the right thing because it's connecting the clouds to the air motion. But climate models don't work like that because they don't work at 20 times larger scales. They work at 2,000 times or 20,000 times larger scales, much, much larger scales. So here, instead of 150 meters, it's 150 kilometers. It's 1,000 times larger, these pieces. And then you cannot connect clouds to motion fields. Instead, you have to kind of guess what the clouds are based on the average temperature in a giant area. And this is what the clouds look like in our climate model. Now, this is not a plot you would normally show anyone because this one doesn't look anything like this one. It's sort of embarrassing. And this is something we've been working on for quite a long time. This is another model that was developed by the German Weather Service. It might be a bit better, but it has no hint of this. If you look a long time, you can find some climate models that do this better, but then they do other things worse. And so trying to piece together how clouds behave and how precipitation behaves in models is a very difficult business, and that's why the models don't work. So what should we do about it? But before we say what we should do about it, now I've given you two examples of how climate models, which you hear all about, how they're based on physics, how they help us understand things, how they're very sophisticated, how they use big computers, how they're, all of this understanding is in them. I've told you two of the biggest problems. I've shown them to you that they have. And you might rightfully sit there and wonder, well, why do we believe all this stuff from these models if they're so bad? And that's people's reaction normally. When they see these things and they say, well, the models are so untrustworthy, why would I believe them? And why would I believe what you said before about climate change? The first reason is that climate change isn't based on these models. It's based on simple theories and observations. And to the extent it's based on these models, the interesting thing is that even though the models are so different, the big picture doesn't change. So the big picture that the world warms because you increase the amount of CO2 and the way it warms, that stays the same. That's like the only thing that stays the same. So the funny thing about CO2 and warming is almost anything you do, that picture stays the same. And that's one reason why climate scientists, despite the fact that the models are so diverse in some respects, actually are even more convinced because the models are in some way here much crazier than the real world. And despite these big differences among the models, they still respond to CO2 in more or less the same way. More or less means a factor of 2. They all warm. If they warm 2 degrees or 4 degrees, that's a debate. So that's why the models being not accurate doesn't really cast into doubt those things that I said we know. So this is a long problem. People have been trying to fix this problem for a long time, to make better models. And it's proven much, much harder than we think. So what do? It's an old problem, and why do we think we can do better? And the reason is that over the long period when people first began developing these types of models until today, computers have gotten faster and faster and faster and faster and faster, till they've gotten to a point now where we can begin to simulate the whole world like those examples I showed which had a good representation of the clouds. So kind of like this, we can simulate the whole world with these clouds on the top rather than these clouds on the bottom. And that's only because computers have gotten to a point where they allow us to represent the world in such small pieces that we can collect the clouds and the precipitation to the motion fields to make really what's a wholly new type of model. And I'll show you an example of that as I zip through here. There. So this is an example of a prototype model that we've been working with in our laboratory, where we simulate the whole world not on a 100-kilometer chunk of pieces, not at a 50 or a 25 kilometer, but a 2.5 kilometer or a 1.25 kilometer grid mesh. And so we can begin to simulate the motion fields which make clouds and make rain, and we don't have to hold our finger in the air anymore and say, well, how does rain really work on average based on these things that we know on average? And what's happened in the last couple years is that not only we can do this, but a lot of groups are doing this. And so here's an example from a paper that we just wrote this year where my group and a group in Japan said, let's take these new models and see how they compare. And as we were doing this, we got calls and emails from around the world saying, oh, we want to do this too, we can do this too. And suddenly we found out that lots of people in laboratories around the world are able to make these prototype models, and there's 10 of them here, and one of them is a satellite picture. I bet nobody here would bet me lunch, unless it's a cheap lunch, on which one is the satellite picture. The point is we've reached a threshold in computing where for short time periods we can simulate the world with much more fidelity and with much more physics than we could ever before. The problem is these models now we were able to run for 40 days and 40 nights. I chose that, 40 days and 40 nights, because I'm not a religious person, but I read somewhere that 40 days and 40 nights is an eternity. So this is infinite, so it's a good amount of time for climate. But the reality is to make these models practical for applying them to climate change, to work through the kinks of running these models. It's not like they will solve every problem. There's a hope that they'll solve some problems. Needs a tremendous effort. But I want to give you a little zoom into what these models behave like, and this is already from something a couple years ago. This is an example of some simulations, but it gives you a sense of how the clouds and the precipitation connect to the motion fields in this type of models in ways that doesn't happen in existing climate models. And this was just the introduction, thanking the EU and the German government and things like this for their support. And here you see hurricanes kind of spinning up here across East Asia. You see lots of things we know. This is also interesting in the real world too. It's very hard to form clouds in deep convection along the equator. So if you look along the middle of the planet, you often see that there's kind of a dark blue where we miss the clouds. These are the storm systems. These storm systems, existing climate models are well designed to represent these. It's more the rain and the clouds that form in the tropics, which they have a hard time with. You see these sort of stratiform clouds off the west coast of the Americas here and here that come and go during the course of the day. And then with the models, you can zoom in like a laboratory, and you can begin to try to understand how the clouds connect to the fluid motion. And so here you see an example. This is the Amazon basin here. And you see these arcs down here on the bottom. These arcs are spreading out. It's when precipitation forms. You know this on a summer day. You're sitting there and suddenly, whoosh, you get a whoosh of cold air, and then the cloud builds up, and you know the rain and the thunder is coming afterwards. We call this a gust front or a cold pool. But these are parts of clouds and storms which are all connected to the motion fields, which in models like this all interact in a very natural way. But in our existing climate models, we have to sort of invent how they behave. And here, this is Barbados, where we're doing our measurements. So we're actually zooming in on those clouds I was telling you about before. So there's Barbados. It's about a 20-kilometer island. And here we're just zooming in on a section. And we go down to scales of 150 meter. That's what I was showing you before, where we simulate good. And here, they don't look very much like clouds. But as the fluid motions develop, you'll see they become much more cloud-like. And the rain's falling down below them. There's some high ice clouds up here. And you see these sombreros, the flat hats where they're spreading out, the ones that grow at night. So we have an ability to much more physically represent the climate system. But it will require an immense cooperation or collaboration among scientists worldwide to take advantage of. And so one way, I'm near the end. I think I have 2 or 3 more slides. So if you're asleep in the back, it's time to wake up now. So in the early days, we had very statistical models. Everything was a statistic, and we made up rules about how everything behaved. And then in the 1950s through 1970s, we developed a way to replace some of these statistical rules with physical rules based on laws of physics. And that was really how heat is transported from the equator to the pole. And that gave birth to this generation of climate models that we still have now. So we could simulate how the heat went from the equator to the pole, but not how the heat went from the surface to the atmosphere. Where we're in the position now is we really have the first models which can simulate the climate. That was one leap that took place in the say late 1960s, and these are the models we've been working with since then. But we're at the position to make another leap here, where we can simulate the scales of motion which transfer heat in the vertical. And climate is all about how to move heat around. And so we can make a great leap. And this great leap allows us to develop models which are much more closely tied to the physics. But it also has another advantage. Right now, when we develop climate models, it's very hard to use data because the climate models don't simulate what you observe. They simulate some sort of average thing, and you observe the actual thing. So you have to translate between, to calculate the average of the actual, or try to infer the actual from the average. But there's this big translation that happens that cuts the communication between people who collect data and people who develop models. In these models, we actually simulate the same scales as you observe. So you connect people who observe the world to people who are trying to simulate or model the world. They're also much closer to impacts. The weather you feel, the weather, for instance, an impact, a lot of people like to talk about carbon. So what happens to carbon? Trees grow. That takes carbon out of the atmosphere. Trees die, and then the carbon goes back in the atmosphere. How do trees die? Do you know how trees die? One of the big ways trees die is the storms blow them down, and then they rot. But to get the storms to blow them down, you need to simulate the storms. And so in these models, you can simulate the scales of motion which influence the climate system in important ways. So they offer the best chance to sharpen the blurry picture of climate change. And hopefully guide prudent action to answer those two other questions that I said in the beginning. The problem is that they're intensive, and to use them effectively requires coordination in institutions and support. But we do this all the time. I mean, as people say, oh, well, you want more money. But my goodness, when you think about climate, it's sort of a paradox. We have 20,000 people in Madrid talking about climate change. And you know what they do it? They do it based on models that are run by university groups. Some professor in some university or some lab in some country says, I have a model, I ran it for the future, I upload it onto a server, compare it with all the other ones. That's not a way of dealing with a serious problem. I mean, no one's accountable. If the model's crappy, who cares? It's on the server, it gets averaged with the other ones. Maybe people will say it's crappy. Everyone wants to have a model, everyone is putting them on there. It's an amateur way of dealing with a serious problem. And when we have serious problems in science in the past, we have serious responses. If we want to understand the basics of matter, what our universe is built out of, we decided it's worth it to take hundreds of square kilometers in the Swiss-French countryside and build an accelerator. Or if we want to look into the origins of the universe, we build observatories, the extremely large telescope that's part of the European Southern Observatory, which is being built here. Fantastic facilities which challenge humanity to do new things and to look in new ways. If we want to look at fusion energy, we build the ITER, the facility. I mean, whether this is a good idea or not, people can debate. There's a project on the human brain. There's European Battery Alliance. There's the measurement of gravity waves. There's new developments in computing. So time and again in science, if we want to solve big problems, we respond as a society to do this as well as we can. And I'm afraid scientifically, we can't say the same thing at the moment. So this is why some of us are saying Europe needs a concerted effort, something that my colleague Tim Palmer calls a CERN for climate science. Which brings me to my last slide, is that yes, we should listen to the science, but if we're going to listen to the science, we also have to be clear about what the science says and what the science doesn't say. And what the science says is that, unequivocally the science says, is that we need to reduce emissions of greenhouse gas if we want to stop making the problem worse. No doubt. But unless we talk about what the science doesn't say, we'll never challenge ourselves to do better. And in climate science, this is the great dilemma, because climate scientists have so often been hesitant to talk about what they don't know, because people use that in a very political debate to pretend that they know nothing. But I've taken the risk that you're more sophisticated than that. And not only the risk, I just have a hard time talking in political ways. As a scientist, it's always about communicating clearly. And so I really don't like the idea of trying to say things in any way other than the way that I see them. And the way I see them now is that there's great challenges for climate science. There's great problems to be solved, but unless we talk about them, we won't do it. So thanks very, very much for your attention. And so I said I would lead the question period, but I know others, sometimes at some point we can take a few questions, and then what I would propose, the organizers will wave their hands if it's a bad idea, is it might be nice that some people want to go and have other things that they have to do, like eat dinner. So I would maybe take a few questions in the beginning, and then let people move on in 5 or 10 minutes, and then stay around for people who want to ask other questions, if that's okay. Okay, so there's a question right here in the middle, and then the question in the back. So first the man in the gray jacket with the blue shirt, and then the woman with the reddish.
Yo quería preguntarle si es usted partidario.
I wanted to ask you if you are in favor of nuclear energy as a temporary, maybe, alternative, because it doesn't emit gas. There are no emissions associated with nuclear. I will repeat. The question is about nuclear power. What do you think? Are you in favor of nuclear power as an alternative? Because nuclear energy does not produce gases or emissions, greenhouse gases. And until we find something more profitable and clean, do you think it's a good option?
So I'm less informed about nuclear. So the question was, what do I think about nuclear power? So for the people who didn't follow the Spanish, which is probably no one, but in case there is someone else like me, the question was, what do we do about nuclear power? It has no emissions, and do I support nuclear power? I will give you a jaded answer, because I haven't spent a lot of time. Mostly I try to understand how the Earth works, and I don't spend much of my research time thinking about alternative energy forms and what's the right balance of mixes. So in that regard, I'm not a very informed source. But I do have the impression that very serious people think that nuclear offers more opportunities to solve problems than we're led to believe. So one of the problems with nuclear that people talk about is proliferation, and another problem is waste. So the argument is, if you can solve the proliferation potential from nuclear, that where people can take the fuel and use that to make weapons, and if you can deal with the waste in an effective way, nuclear becomes a much more attractive alternative. And the argument of the people who are developing nuclear is that there are technologies to do that, where you can reduce the half-life enormously, and you can make very low-grade waste that doesn't have the weapons potential. I can't evaluate those arguments. That's science, I don't know, but that's the argument. And nuclear is stigmatized in society to a point where we can't discuss it effectively. And so as a result, people like me, for example, are uninformed. So all I would say is, I do think it would be a mistake not to think seriously about all options. And whether or not the claims of the people who think nuclear is a viable solution are true, is probably something we need to spend more time thinking about. So that's about the best I can answer you there. So the woman in behind is.
Without the support of countries like China or those superpowers that emit so much carbon, all of these studies and all of this effort, is it useless?
Yeah, probably. You know, that was in this very first slide. If I went to it, I wonder if it still clicks. Here, what Nordhaus said, this is 1977. You know, if you read what he says, how can we, right here, how can we reasonably hope to negotiate an international control strategy among the several nations with widely divergent interests? That was as true then as it is true today. So the extent to which countries perceive an interest in doing something rather than just talking about something. So it's a wonderful strategy for countries to talk about a problem, because it makes it seem like they're solving it. And so if I didn't want to do anything about climate change, I would talk about it all the time, because it would sort of distract people from the issue. So, you know, unless countries all agree that they have to do something, it will be very hard. Nordhaus also argues, and I think effectively he argues from an economic point of view. Again, this is not my field, I can just tell you what he argues. He argues that we should use things like climate projections as a trade mechanism. So we should try to form blocks of countries who say this is our cultural norm, just like we don't accept child labor. So we shouldn't trade on equal terms with countries which don't practice good stewardship for the environment. Whether that would work, that's a debate for the economists, but I do think it points to a particular problem, and one that concerns me a lot these days, is that if you name a problem, it often has something to do with the effects of humans to act globally. So we can act globally in so many ways, whether it's polluting CO2, whether it's putting plastic in the ocean, whether it's accumulating wealth. I mean, the way some people accumulate a massive amounts of wealth is by scaling their activities globally. And these problems we have a very hard time controlling because we can't govern globally. So before, when we lived locally, if you misbehaved locally, then you would be controlled locally, right? So if you throw your garbage onto the street, then you get in trouble. Now you can globally act, but we have very little ability to globally influence people's actions. And so your question, it's a very long answer to saying, yeah, this is the problem we have to solve. Here we had a question, and then I would take, I know some people like it to have their questions in the general audience, so I would maybe take after this one 2 more if there's 2 more, and then we'd let people go have a good dinner.
No sé si puede poner la diapositiva.
Could we see the slide of climate sensibility or sensitivity? I think it was number 9 or number 6. Number 5 or number 6. The different models were, yeah, this one. Right. It seems that in the 6th review of climate sensitivity, it's not just gone up, but there is greater scatter. Now, the question is the following. The report of the 2018 ICCP report says that there's a limit of about 500 gigatons to increase temperature by 1.5 degrees and 1,100 for an increase of 2 degrees. But I suppose it's been made or done with model number 5. But with model number 6, those global emissions, which I presume are the basis for climate negotiations, are lower than the ones that were published last year. IPCC published in October 2018. I would like to know your comments, have your comments about that.
The question was that when you think about how much carbon, and you can correct me if I get the question wrong, but the question was, if you think about how much carbon we can emit before the temperature increases a certain amount, it depends on how far, I have so many tools here, on this graph, it depends on this climate sensitivity. So if a model is very sensitive, that means you can't emit very much carbon before you'll reach that temperature that you want to avoid. And if it's very unsensitive, that has a low sensitivity, that means that you can emit quite a bit more carbon, in this case 2 or 3 times more, before you reach that threshold temperature. And so in the IPCC, this intergovernment panel that tries to collect understanding of where the science stands, they give us estimates of how much carbon we can emit before the world will be globally 2 degrees warmer. And their last report was based on, to some degree, these sorts of models. And here you see the models got a bigger spread, which means we're less certain. If you just go from these models, we're less certain than we were before. And if anything, it says that some models are suggesting we've already emitted more carbon than we're allowed to emit to have a 1.5 degree world. The good thing is that we know, for one, we know there's no good reason to take these models at face value. For the reasons I showed, they behave on they depend on clouds in ways that I showed before. And when you look at the models with the higher sensitivity here, almost all but at least one are quite obviously out of whack. So out of whack means if you look at the warming in a graph like this, where you just plot the warming with time, all of those models with the high sensitivity are warming much faster than the world is warming over the past 30 years. So there's good reasons to discard those models. But that's kind of a sad state of affairs when we've spent 30 years trying to make models better, and now all we can say is, well, actually now we know enough to throw which ones away, which is sort of the position we're in right now. So you're right. If you would just believe that graph, the models with the larger sensitivity suggest that we have much less CO2 to emit than we thought. There's good reason not to believe those models with the high sensitivity. But don't get me wrong, we still don't have very much carbon to emit before the world, if we decide 2 degrees is warm enough, we're quite near the boundary and we need to reduce carbon rather urgently. Okay, so I said I would take 2 more, and there was, I had here, and then I had one in the front. There's a tendency for men to like to ask questions more than women, so I'd make an exception if there's any women who want to ask a question, but you shouldn't feel compelled, because I know not everyone likes to ask questions. Okay, so we have, if you're really tired, you can sneak out, no one will bother you, but there's 2 more questions here, and then we'll call it to end. 1, 2, 3, 4, then we'll stop. Okay.
Perfect. First of all, thank you very much for this really interesting presentation. My question would be related to ecosystem damages. We see now that there's a lot of ecosystems which are locally impacted by, let's say, warming waters. For example, coral reefs. My question is, how well are predictions for ecosystem collapse, for example, of coral reefs, connected to those elaborate climate models that you just presented, kind of relating to those very localized effects of storms and warm water fields?
So the question was, well, I think that was translated, but I'll repeat it again just for myself. The question was ecosystems. If we look at local ecosystems, how much do they depend, or how well are they predicted by the type of models that we're talking about? And the answer is not very well at all. So if you take a traditional climate model, there's almost nothing that we can use its output to directly predict. Because what happens is it will get the ecosystems like coral reefs are very sensitive to small changes in the sea surface temperature. And if you look at climate models, even the mean sea surface temperature, so if you take in this comparison that we had here, if you take these models, this is how much the temperature changes with warming. But if you ask them what their temperature was for the 20th century, they differ by 5 degrees. Because it's very hard to get the actual Earth's average surface temperature of about 15 degrees Celsius. Some will be 18, some will be 13. So the range in just the base temperature is much bigger than the sensitivity that many of the ecosystems have. And for that reason, we never look at the absolute temperature. What we do is we call it a bias correction. So we subtract out the error. But me and my co-author, who I mentioned before, Tim Palmer, if the Earth really is that fragile, if things collapse because of small temperature changes of 2 degrees, then what can it mean to have a model which is 3 degrees off in the base state to begin with? Because all of those things should have collapsed already. So we have this contradiction in the science that the models are very, they're I don't know. They're on one hand, they're fascinating and interesting and simulate many things, but when you look at detail, they have many problems that we try to correct as best we can, but it makes them not a very reliable tool to look at some of the questions that you mentioned. So I hope I answered that. So regionally, the models have very little specificity, and the only way we get specificity out of them is to correct them for their biases. So here, and then we had the 2 questions here.
Thanks for your talk. I would like to ask you two questions in one. One is now connecting with this question, what about whether the biological systems will have some buffer effect on all your climate models. And the second is whether you will be able, with these new computers and so on, to detect tipping points in your models.
Yeah, so the question is, do the biological systems have buffers, and will we be able to detect tipping points? And to me, that's the real question, because it depends which ear you use to listen to the debate. Depending on who you are and which newspapers you read, you could have the feeling that the world is doing absolutely nothing about climate change. No one's talking about it. It's a problem, and absolutely nothing's happening. And in some ways, that's right. And you could also view that climate change is all exaggerated and people are making a big deal about everything, you know, like the forests dying or people starving in the 70s. It's just another example of environmental alarmism run amok. So I think some people have that view. There's other people which have the view that we're headed to a catastrophe, that if the temperature goes another ½ degree, that we'll sort of fall over the edge with tipping points. Suddenly we increase the temperature. The scientific evidence for tipping points is super thin. It comes to this idea that somehow there's a cliff, that suddenly the climate system behaves quite differently. There was a paper that's gotten a lot of press the last couple of days, and they take 7 or 8, who knows, maybe there's an author in the audience and they can disagree, but they take about 7 or 8 tipping points. These are kind of catastrophic changes that happen regionally, and they connect them all together. And they outline what might be the worst case scenario. But every single one of these is very, very unlikely, and the fact that they're connected in the way that these authors suggest is also unlikely. So the best you could say is that's the very worst case, and everything that we have, that we know to date, doesn't really support the idea that the world is that fragile. But we don't really have good tools. And their answer would be, do we really want to take that risk? It might be tiny, but the implications are catastrophic. So that's another reason, just to have an effective public debate, I think we need much better tools, because otherwise we're just left with this wild speculation about some people saying the world's ending tomorrow and other people saying you're being hysterical, and then we don't have a really good discussion. So the woman on the far right, and then you in the red as second.
Has got the sunspots a rule about the climate?
Can you say once more time the first part, the rule?
The spots on the sun.
Do you know the sun has got spots, manchas, spots?
Pulsar. Oh, sun.
So the activity of the sun has got a rule on our climate.
Yeah. So the question,
scientists who were not.
yeah, I think I can repeat.
Okay.
I know what you're talking about. So there have been some scientists, Scandinavian scientists, who have argued that cosmic rays from the sun have an influence on cloudiness, and that affects climate. And there's an argument that sunspots are changing and solar activity influences the climate. And the main argument about that is that the changes that we would expect, if that were true, other than just the warming, don't happen. And particularly in the upper atmosphere, because these changes in sunspot activity are very strong at wavelengths which are absorbed in the upper atmosphere. So we don't see changes there that we would expect if it was having the role that it would have. And the other thing about the sunspot activity is it doesn't explain one of the telltale signatures of CO2. You know, when we first had the idea that CO2 is causing warming, you could have thought of many other reasons. You could have said, well, the heat's coming out of the ocean, or the development of the land surface is affecting things, or it's the sun. I mean, there's a whole list of things that people tried to work through and think through, and one of them is its changes in solar activity. But the problem with the solar activity is that when you have more CO2 in the atmosphere, the upper atmosphere, the stratosphere, cools. And the troposphere, the lower atmosphere, warms. So you have these two different signals. And that comes from carbon dioxide, but it doesn't come from changes in the sun. So there are some people who develop elaborate arguments which suggest that there's cosmic rays which are just changing clouds in just the right way to explain the observed effects. But I think they're about the only ones who believe themselves, because there's been very little corollary evidence to support their claims. Yeah. So the last question, then you really get to go have dinner, is from the woman in front.
I'll do it in Spanish.
It's almost a comment rather than a question about the scientific dissemination of things. I found it very interesting what you proposed about the fact that we should be talking about what we don't know about yet in order to make progress. But of course, it depends. The debate, there are different audiences. Some are more trained, others are less trained. And the people who are responsible for policies are often not interested in talking about these things that we have to learn more about. So it's a very difficult situation. And also this idea of joint work between scientists and alliances to make more progress in areas that we don't know enough about. Don't you think that should be limited to the academic world more or scientific world more? People like us here who are interested. Scientific dissemination should not should work more on areas there where we don't have the knowledge. We have to get that. We have to develop knowledge. And we also must make people, I think, aware of the fact that we need a more sustainable way of life. And we have data enough to be able to say that the life that we're living is not really sustainable. I don't know whether it was a bit confusing, but I hope you understood me.
Not confusing at all, and it was a perfectly sensible comment, which is how do we communicate science in the public? And this is something that climate science struggles with. And overall, we've taken the approach of saying, let's talk only about those things that we know. And what's happened as a negative consequence of that is that people don't appreciate what we don't know. And two things happen, is that getting young people into the field is difficult because all we talk about is what we know. And young people are fascinated to solve problems that we don't know the answer to. So imagine if you're talking to a general public audience, you have to give through the media and through the public a sense that there's big problems that young people can solve, and that society also needs to support this adventure into the unknown. And climate is partly an adventure into the unknown. But at the same time, you don't want to threaten the consensus to take very responsible action about big problems. And so I'm trying to walk this divide, but I'm practicing this. I'm not sure if it's a good idea in the end. Maybe in a few years I'll realize this was the wrong approach. But I do think as scientists, the most important thing is to try to speak clearly and candidly. And as activists or politicians or community activists or organizers, there I think it's much more easy to talk in a more targeted way to get action. But if the scientists don't talk in very frank ways, then we leave the society a little bit vulnerable. So that's my thinking. I might be wrong on that. Your comments are very well taken. It's an experiment. See how it turns out. And I'd like to thank everyone for their attention and a great night. And like I said, I'm happy to talk one-on-one to anyone.